I'm doing it anyway, and a blind student once said that I do this when I'm just about to submit the final version of a paper. I'm doing it anyway, and a blind student once said that I should record this so that he could listen to papers. So I'm doing this experiment, and a couple hundred people watch these videos, and so if you are benefiting from these, do let me know, and I'll keep doing this. Like the video, it lets me know that this is appreciated. So today I'm reading multi-step reasoning over unstructured text with Beam Dense Retrieval. This is work primarily by my student Chin in collaboration with folks at Microsoft. Complex question answering often requires finding a reasoning chain that consists of multiple evidence pieces. Current approaches incorporate the strengths of structured knowledge and unstructured text, assuming text corpora is semi-structured. Building on dense retrieval methods, we propose a new multi-step retrieval approach, Beam DR, that iteratively forms an evidence chain through beam search in dense representations. When evaluated on multi-hop question answering, Beam DR is competitive to state-of-the-art systems without using any semi-structured information. Analysis further indicates that through query composition in dense space, Beam DR captures the implicit relationships between evidence in the reasoning chain. The code is available at a link in the description. Section 1, Introduction. Answering complex questions requires combining knowledge pieces through multiple steps into an evidence chain. Ralph Hefferline has a connection to Columbia University, can help you answer a question, as we'll see in an example in Figure 1. When the available knowledge sources are graphs or databases, constructing chains can use the source's inherent structure. However, when the information needs to be pulled from unstructured text, which often has better coverage, standard information retrieval, IR, approaches only go one hop from a query to a single passage. Recent approaches try to achieve the best of both worlds. Use the unstructured text of Wikipedia with its structured hyperlinks. While they show promise on benchmarks, it's difficult to extend them beyond academic testbeds because real-world datasets often lack these tools. For example, medical records lack links between reports. Let's take a look at Figure 1. At top, we have a complex question example from HotPot QA that requires finding an evidence chain to answer the question. At the bottom, Beam DR iteratively composes the new query and retrieves evidence in dense space without the need for linked documents. Dense retrieval provides a promising path to overcome this limitation. It encodes the query and evidence passage into dense vectors and matches them in the embedding space. In addition to its efficiency, thanks to maximum inner product search, Xiong et al. Showed that dense retrieval rivals BERT-based retrieves and re-rank IR pipelines on single-step retrieval. Unlike traditional term-based retrieval, fully learnable dense encodings provide flexibility for different tasks. This paper investigates a natural question: can we build a retrieval system to find an evidence chain on unstructured text corpora? We propose a new multi-step dense retrieval method to model the implicit relationships between evidence pieces. We use beam search in the dense space to find and cache the most relevant evidence chains, and iteratively compose the query by appending the retrieval history. We improve this retrieval by encouraging the representation to discriminate hard negative evidence chains from the correct chains, which are refreshed by the model. We evaluate Beam Dense Retrieval, BeamDR, on HotPot QA, a multi-hop question answering benchmark. When retrieving evidence chains directly from the corpus, full retrieval, BeamDR is competitive to the state-of-the-art cascade re-ranking systems that use Wikipedia links. Combined with standard re-ranking and answer span extraction modules, the gain from the full retrieval is propagated to the answer accuracy. Qualitative analysis shows that by iteratively composing the query representation, BeamDR captures the hidden semantic relationships in retrieved evidence. Section 2, Beam Dense Retrieval. This section first discusses the preliminaries for dense retrieval, then introduces our method, Beam DR. Section 2.1, Preliminaries. Unlike classic retrieval techniques, dense retrieval methods match distributed text representations rather than sparse vectors, with encoders, BERT for example, to embed query Q and passage P into dense vectors, EQ and EP. The relevant score F is computed by a similarity function, sim, e.g. Dot product over two vector representations. So in this case, the function for the similarity between Q and P is the similarity of the underlying encodings of the query and the passage. After encoding passage vectors offline, retrieval is efficiently conducted by approximate nearest neighbors search that finds passage vectors with maximum inner product with the query. In other words, MIPS. Section 2.2, Finding Evidence Chains with Beam DR. We focus on finding an evidence chain from an unstructured text corpus for a given question, often the hardest part of complex question answering. We formulate it as a multi-step retrieval problem. Formally, given a question Q and corpus C, the task is to form an ordered evidence chain P1 to Pn from C with each evidence a passage. We focus on the supervised setting, where the labeled evidence set is given during training, but not during testing. Finding an evidence chain from the corpus is challenging because passages that do not share enough words are hard to retrieve. For example, in Figure 1, the evidence Columbia University. 2, if you miss one evidence, you may err on all that come after. We first introduce scoring a single evidence chain, then describe how to use beam search to find top K chains, and then finally discuss training Beam DR. Evidence chain scoring. The score, Sn, of an evidence chain P1 to Pn is the product of the normalized relevant scores of individual evidence pieces. At retrieval step T, to incorporate the information from both the question and retrieval history, we compose a new query, Qt, by appending the tokens of retrieved chains P1 to Pt-1 to query Q. We use MIPS to find relevant evidence PT from the corpus and update the evidence chain ST by multiplying the current step's relevant score by the total. Beam search in dense space. Since enumerating all evidence chains is computationally impossible, we instead maintain an evidence cache. In the structured search literature, this is called a beam. The k-best scoring candidate chains we have found thus far. We select evidence chains with beam search in dense space. At step T, we enumerate each candidate chain j in the beam, pj of 1 up to pj of t-1, score the top k chains, and update the beam. After n steps, the k highest scored evidence chains with length n are finally retrieved. Training Beam DR. The goal of training is to learn good embedding functions that differentiate the positive, relevant, and negative evidence chains. Since the given relevant evidence pieces are not ordered, we sample positive permuted evidence chains from the gold evidence set. We define negative chains as those with at least one evidence piece not in the relevant evidence set, which are sampled from the corpus. For each step T, the input consists of the query Q, a sampled positive chain, capital P plus subscript T, consisting of little p positive 1 to p positive t, and M sampled negative chains, big P minus j comma t, consisting of little p, 1 negative up to pt negative. We update the negative log likelihood loss, where we exponentiate the score of the positive evidence chain and then divide that by the normalized sum over both the positive and the negative. Rather than using local in-batch or term matching negative samples, we follow Gu et al. And select negatives from the whole corpus, which can be more effective for single-step retrieval. In multi-step retrieval, we select negative evidence chains from the corpus. We use beam search inference on the training data to find the top k highest scored negative chains for each retrieval step. Since the model parameters are dynamically updated, we implement this strategy by asynchronously refreshing the negative chains with the up-to-date model checkpoint following Gu et al. And Xiong. Experiments. Section 3, Retrieval and Answering. Our experiments are on the HotPotQA full wiki setting, the multi-hop question answering benchmark. We mainly evaluated on retrieval that extracts evidence chains, passages, from the corpus. We further add a downstream evaluation on whether it finds the right answer. Section 3.1, Experimental Setup. Following Asai et al., we report 4 metrics on retrieval. Answer recall, AR, if the answer span is in the retrieved passages. Passage recall, if at least one gold passage is in the retrieved passages. Passage exact match, PEM, if both gold passages are included in the retrieved passages. And exact match, EM, whether both gold passages are included in the top 2 retrieved passages, i.e. the top chain. We report exact match and F1 on answer spans. We use a BERT-based encoder for retrieval and report both BERT-base and large for span extraction. We warm up BeamDR with TF-IDF negative chains. The retrieval is evaluated on 10 passage chains. Each chain has 2 passages, to compare with existing retrieve and re-rank cascade systems. We train a standard BERT passage re-ranker and evaluate on 10 chains re-ranked from top 100 retrieval outputs. We train BeamDR on 6 2080 Ti GPUs, 3 for training, 3 for refreshing negative chains. We do not search hyperparameters and use suggested ones from Xiong et al. Section 3.2, Passive Chain Retrieval Evaluation. Baselines. We compare BeamDR with TF-IDF semantic retrieval, which uses a cascade BERT pipeline, and the graph recurrent retriever, our main baseline, GRR, which iteratively retrieves passages following the Wikipedia hyperlink structure and is state-of-the-art on the leaderboard. We also compare against a contemporaneous model, Multihop Dense Retrieval, MDR. Let's take a look at Table 1. Compare BeamDR with other retrieval systems. Top, retrieval from the whole corpus. Bottom, re-ranking the top 100 full retrieval outputs. A star indicates parallel work. Let's take a look now at Figure 2. Passage retrieval accuracy on different beam size. Our system is relatively robust to beam size. Results. Robust evidence retrieval without document links. Table 1 presents retrieval results. On full retrieval, BeamDR is competitive to GRR, a state-of-the-art re-ranking using Wikipedia hyperlinks. BeamDR also has better retrieval than the contemporaneous MDR. Although both approaches build on dense retrieval, MDR is close to BeamDR with TF-IDF negatives. We instead refresh negative chains with intermediate model representations, which helps representation learning better discover evidence chains. Our ablation study, Greedy Search, indicates the importance of maintaining the beam during inference. With the help of cross-attention between the question and the passage, using BERT to re-rank BeamDR outputs outperforms all baselines, as expected. Varying the beam size. Figure 2 plots the passage EM with different beam sizes. BeamDR is robust. Section 3.3, Answer Extraction Evaluation. We compare BeamDR with TXH, GRR, and the contemporaneous MDR. We use release code from GRR, following settings on BERT, base, and large. We use 4 1080 Ti GPUs. Using the same implementation, but on our re-ranked chains, BeamDR outperforms GRR, suggesting gains from retrieval could propagate to answer span selection. BeamDR is competitive with MDR, but slightly lower. We speculate different reader implementations might be the cause. Exploring how we hop. In this section, we explore how BeamDR constructs evidence chains. Section 4.1, Qualitative Analysis. Figure 3 shows query and passage representations with t-SNE. Unsurprisingly, in the dense space, the first hop query, question, is close to retrieve passages, but far from second hop passages, with some negative passages in between. After composing the question and first hop passages, the second hop queries indeed land closer to the second hop passages. Our quantitative analysis, Table 3, further shows BeamDR has little overlap between retrieved passages and two hops. BeamDR mimics multi-step reasoning by hopping in the learned representation space. Section 4.2, Hop Analysis. To study model behaviors under different hops, we use heuristics to infer the order of evidence passages. In Table 3, BeamDR slightly wins on first hop passages with the help of hyperlinks. GRR outperforms BeamDR on second hop retrieval. Only 22% of the top 10 BeamDR chains are connected by links. BeamDR wins after using links to filter candidates. Section 4.3, Human Evaluation on Model Errors and Case Study. To understand the strengths and weaknesses of BeamDR compared with GRR, we manually analyze 100 bridge questions from the Hotpot QA development set. BeamDR predicts 50 of them correct, and GRR predicts the other 50 correctly. We further include a case study in Table 5. Table 2, Hotpot QA dev and test set answer exact match and F1 results. The star indicates parallel work. Figure 3, t-SNE visualization of query Q and passage P embeddings over different retrieval steps. BeamDR conducts multi-step reasoning by hopping in the learned representation space. Strengths of BeamDR. Compared to GRR, the largest gain of BeamDR is to identify question entity passages, as there is often little context overlap besides the entity surface form. A term-based approach, TF-IDF used by GRR, falters. Some of the GRR errors also come from using reverse links to find second hop passages, i.e. the second hop passage links to the first hop passage. Weaknesses of BeamDR. Like Karpuchen et al., many of BeamDR's errors could be avoided by simple term matching. For example, matching what screenwriter with credits for Evolution co-wrote a film starring Nicolas Cage and Tia Leone to the context, Family Man is a 2000 American film written by David Diamond and David Weissman starring Nicolas Cage and Tia Leone. Her name is Tia, not Ta, right? Section 5, Related Work. Extracting multiple pieces of evidence automatically has implications from solving crossword puzzles, graph database construction, and understanding relationships to question answering, which is the focus of this work. Given a complex question, researchers have investigated multi-step retrieval techniques to find an evidence chain. Knowledge graph question answering approaches directly search the evidence chain from the knowledge graph, but falter when KG coverage is sparse. With the release of large-scale data sets, recent systems use Wikipedia abstracts, the first paragraph of a Wikipedia page, as the corpus to retrieve the evidence chain. Dingra et al. Treat Wikipedia as a knowledge graph, where each entity is identified by its textual span mentions, while other approaches directly retrieve passages. They first adopt a single-step retrieval to select the first hop passages, for entity mentions, then find the next hop candidates directly from Wikipedia links and re-rank them. Asai et al. Conduct beam search to find the chains and achieve the best results. BeamDR retrieves evidence chains through dense representations without relying on the corpus's semi-structure. Chi et al. Iteratively generate the query from the question and retrieve history and use traditional sparse IR systems to select the passage, which is complementary to BeamDR. Let's take a look at Table 4. We manually analyze 100 bridge questions and categorize the model errors. Let's take a look at Table 5. Case study of BeamDR and GRR retrieval, text-based retrieval approaches, The TF-IDF used by GRR is unable to distinguish two players with the same name. BeamDR correctly identifies the question entity. Section 6, Conclusion. We introduce a simple, yet effective, multi-step dense retrieval method, BeamDR. Beam search and globally refreshing negative chains during training allows BeamDR to find reasoning chains in dense space. BeamDR is competitive to more complex state-of-the-art systems, albeit not using semi-structured information. While BeamDR can uncover relationships embedded within a single question, future work should investigate how to use these connections to resolve ambiguity in the question, resolve entity mentions, connect concepts across modalities, or to connect related questions to each other. If you've made it this far, thank you very much for listening to another paper read out loud by me as I do my final editing pass. If you enjoy this, please leave a comment, like the video, let me know, and if people do appreciate this and find it useful, I'll continue to do it.